Hi, I'm Joey Broussard, a postdoctoral fellow in the lab of Sam Wong at Princeton University. One of the primary drivers of my research is development and understanding of genetically encoded tools, like the calcium sensor GCaMP. Today I'm going to tell you about an effort that we in the Wong and DiGregorio labs have undertaken to better understand how GCaMP signal changes in calcium. In particular, we compare the popular fast sensors GCaMP 6F and JGCaMP 7F with JGCaMP 8F, the latest fast GCaMP developed in Lauren Luger's lab. GCaMPs have become common tools in the arsenal of systems neuroscientists who want to survey the activity of large numbers of neurons in behaving animals. But interpreting what those signals mean in terms of spike number and timing remains a challenge. In an effort to understand how GCaMP transforms spike-driven calcium transients into fluorescent observables, we track fluorescent responses to calcium in two controlled systems. First, we looked at the ex vivo response of parallel fiber boutons to applied spikes. In this system, we compared GCaMP responses to those of a linear synthetic indicator, Oregon green Bapta5N, to detect any nonlinearities imposed by the GCaMPs. We then recorded the response of GCaMPs to calcium clamps applied in a stop flow device in an attempt to understand the nonlinearities we uncovered in our ex vivo dataset. Before going into the details of those nonlinearities, it's worth noting that we characterized the performance of the three GCaMPs and their ability to detect single spikes. We found that JGCaMP 8F gives a significant boost to single spike detection both because it's faster than 6F and 7F and because it reports spikes with better signal to noise. That said, we were intrigued to find similarities in the way that the different GCaMPs transform the calcium signal. For instance, we found that all GCaMPs, but especially 6F and 7F, have a larger response to the second of two spikes applied with a 10 millisecond interval. To understand why GCaMPs react this way, we took stop flow recordings with steps of increasing calcium concentration. We found that the three tested probes had a steep dose response curve to calcium. We quantified the degree of cooperativity exhibited by each probe using fit-Hill coefficients. Across both systems, 6F was the most nonlinear, while 8F was the least. We also investigated how application of multiple spikes in quick succession to GCaMP expressing boutons affects the rate of fluorescence decay. We applied a single spike to image boutons, then followed that with 10 spikes at 100 Hz to the same structure. When we aligned the traces by when the final spike was applied, it became clear that all three GCaMPs had slower decaying fluorescence than in the single spike trials. In stop flow, changing the initial calcium conditions did not affect the rate of fluorescence decay. This suggested a more complex interplay between GCaMP and calcium dynamics is responsible for the ex vivo use-dependent slowing effect. To further understand the dynamics of the GCaMP response, we fit responses to either a double or single exponential. In all probes, individual traces were better described by a double exponential fit as demonstrated by the adjusted R-squared values for the fits. This suggests that multiple processes occurred during GCaMP's response to calcium. In addition, the time constants of the slower exponential component were much slower than we would expect given the rapid decay of fluorescence achieved by fast GCaMP indicators. This suggests that GCaMP does not decay by the same route as it increases its fluorescence. Putting together our findings, we propose a model of GCaMP to help explain its responses in both the cellular and in vitro contexts. The model consists of a fast and slow process, each of which undergoes calcium binding prior to a fluorescence transition. Based on the cooperativity that we see in our ex vivo and stop flow data, we used a Hill equation for the calcium binding process. From our analysis of the kinetics in stop flow, we split the fluorescence between a fast and slow process. We further linked these processes kinetically so that the slow process decay isn't entirely dependent on the slow process kinetics. Bouton simulations with the stop flow based model recapitulate the slow decay we saw in our ex vivo dataset. Tracking model states, we found that the slow decay is due to the accumulation in the slow process during prolonged periods of elevated calcium. Additionally, we were able to fit the model to a 10 Hz Poisson stimulus response. In summary, we demonstrated the advantages of JGCaMP 8F for single spike detection relative to 6F and 7F. We showed that despite these advantages, there are qualitative similarities to how the GCaMPs we tested transform a calcium signal to a fluorescent observable, both in terms of amplitude and kinetics. We modeled that process to gain quantitative insight into how the different GCaMPs produce the observed nonlinearities. Finally, the Wong lab at Princeton is on the lookout for postdocs. If you're interested, contact Sam Wong directly at the email address shown.